Hello, everyone. Reminder that Lab 6 is due Thursday evening, so hope you're noodling away on that if you haven't finished it already. It will take some time to get it all working, so I'd recommend getting a start really soon if you haven't already. So today we're going to do what I think is one of the more fun lectures. We have an interesting engineering problem to solve, and we'll actually come up with a nice, elegant solution for it, which is a pleasing combination. So away we go. So the problem we're going to tackle today is a little bit about how to do inter-process communication, or more specifically, how to arrange the synchronization between two communicating processes so that the operations performed by the processes happen in the correct order. And by correct, you'll see what I mean by that in a second. So this is something that happens pretty much all the time in computers. We're forever sending information from one place to another, and we have the notion of a producer that produces the information and a consumer that consumes it, and then information flows over this wire here from the producer to the consumer, and we actually have to coordinate the interactions between the producer and the consumer so that the producer doesn't overwhelm the consumer with too many things, and which might get lost depending on how much buffering we have, and the consumer doesn't try consuming things that haven't been produced yet. And you can say, well, that's sort of obvious, but remember, programs are pretty dumb. They'll just go get to a memory location and fetch whatever's there. So we're going to have to figure out how to do the appropriate signaling to say, please look here in this buffer that we're sharing as we communicate from one process to another, some sort of shared data or perhaps a pipeline of some sort. And what we want to do is talk about how each of these processes manage their end of the pipeline and communicate to the other process that there's something there to take or that something has already been taken. So it's really a signaling exercise that we're going to be doing today. And we'll come up with, as I say, I think what will be a reasonably elegant solution. So this type of producer-consumer problem crops up in most applications. For example, most of the applications that you run use a separate thread for the user interface, and the user interface produces a sequence of events that need to be queued up and processed by the front end, and then often, as in, for example, JSIM, there's a back end where the simulation is happening. So there's sort of the event processing, to the front end, and then from the front end to the back end. These are all sort of communications paths that have to be managed, and some amount of synchrony between the actions in one and the actions in the more background tests. Okay. So conceptually, imagine that the producer is running in a loop which does a lot of complicated calculation represented by XXX, and then occasionally it's going to send some information, maybe a particular character, to the consumer, and then it goes back and enters its loop again. And the consumer is in a loop where it receives a piece of information, so it will get the character that the producer sent, and then process it somehow, and when it's done with the processing of the communication, the message it just received, it will go back and look to receive another message. So these are the two, these are running independently, right? So the idea is that this is running in one process, this is running in the other, and there is a communication channel between them, which is maybe the shared memory location or the communication channel that will convey the characters, and the question is, what else do we need to convey? What other control signals do we need to have to organize the communication so it behaves correctly? So imagine time running down the page, and you can see what the producer is going to do is a calculation that produces the first character, which is then sent to the consumer, and then the producer, because he's in a loop, goes and produces the second character and sends that, so forth and so on. So here's time sort of running down the page for the producer. Over in the consumer, we see a receive followed by some calculation, followed by another receive. And what we're going to want to do now is explore, so each of these is sort of running independently, but there's going to be some relationship about what can execute when in one program and the other, one process and the other. So we're going to introduce a notion of precedes, this sort of what's called a precedence relationship. In this case, we use this fancy little sort of less than symbol to say that alpha precedes beta. So that's a very abstract way of saying, look, it comes before, and we want to ensure that happens. And so, in fact, there's two precedence constraints that we're interested in. The first one of which is that clearly you shouldn't receive a character before it's sent. In other words, we expect that the receive statement in the consumer will execute for the first time after the first time the send statement has executed in the producer. Right, so we want to somehow establish the precedence relationship that the first send happens before the first receive. And that's shown by the solid arrows here. There's a second relationship that we might want to ensure in the case where we only can transmit a single character at a time. We have a very thin wire that goes between them. I can send you one character, but I'm not allowed to send anything more until you've consumed the first character. And so we might also want to introduce the precedence constraint that the second send has to wait until the first receive happen. And so what you can see is that we've established a series of precedence constraints that don't constrain when XXX happens, or YYY happens relative to XXX, relative to what's happening in the process. The only constraints about allowable execution orders are between the send and receive, and then the receive and the subsequent send. Everybody sort of get that? So what we want to do is to come up with some way in which the producer and consumer can signal each other, letting them know, okay, I've sent you a character, and then you as the consumer might want to signal me back as the producer that, okay, I've consumed the character, you can go ahead and do the next one. So we're coming up with sort of a way of managing our communication channel that's shared between us. That particular problem isn't so interesting, so what we're going to do is complicate it a little bit. We're going to introduce a first in, first out buffer between the two, so it has n characters. And what that allows us to do, so first in, first out means is, in terms of the consumer's point of view, when it asks for the next character, it will get the earliest character that's still in the buffer. So with a FIFO buffer, as the producer puts things in to the buffer in a certain order, the consumer, when it asks for things from the buffer, will get them in the same order that the producer produced them. So there's no mixing of order with the buffer. And by putting in this FIFO buffer between the producer and the consumer, we will allow the producer to get up to n characters ahead of the consumption. So if we had an n character buffer here on the table between me, the producer, and you, the consumer, I could put the first character there, and whereas before I had to wait for you to consume it because there's only room for one in the buffer, now there's room for n characters in the buffer. So I can go ahead and produce the second character and the third character, so forth and so on, up to n, and at that point I have to stop because I filled up the buffer, but it allows some elasticity between the running of the producer and the running of the consumer. So the producer might run for a little while, produce 3 or 4 characters, and then the consumer might consume a couple characters. So we don't have the producer and consumer quite in lockstep, and we allow an n character difference between where the producer is in its loop and the consumer is in its loop. Okay. So we're going to relax this precedence constraint and simply say that the ith reception has to happen before the ith plus nth send. In other words, we're going to let the send get ahead by n steps. Okay, but at that point you're stuck. Once you get to you've sent n things, you have to wait for at least the first reception to happen before you're allowed to do the nth plus first send. In other words, the reception has made room in the n character buffer for you to send one more character. So the way this might work is, so we have a read pointer and a write pointer. So this is a little circular buffer, which means we'll go through from right to left, and when we fill up the third thing, we'll go back and we'll just start filling up again at the first entry in the buffer. So that's what we mean by circular. It's just a fixed length buffer, and we have pointers that tell us where the reading is happening and where the writing. So we go off and we do a bunch of sends in a row, and you can see that the right pointer is busily advancing, and we're slowly filling up the buffer. And at this point, the buffer is full. So capital N is 3 in this case. Now the producer cannot produce any more characters. We can't do any more sends. We're sort of stuck waiting for the first receive. So the first receive happens, and you can see it has a separate read pointer. that tells it where the next character to read is in the buffer. And so these pointers will basically just chase each other round and round and round the circular buffer, and hopefully won't lap. So the producer needs to stop when the buffer is full, and obviously the consumer needs to stop when the buffer is empty. But any other combination, they both have an opportunity to run. Now that the first receive has happened, or in fact a couple receives in this case, we can go off and do some more sends and some more receives. Everybody sort of happy with that let me go back to that sort of scenario, and notice that because we have an n character buffer, we can get up to 3 sends ahead of where the receive is. Okay? So here's some code that represents that sort of graphic on the previous page. So there's a shared memory which holds the buffer and the input and output pointers. So that's the thing we're going to, so the input and output pointers in this case are just an index into the buffer. So the index can go between 0 and n minus 1. Right, so that would allow me to access any one of the n locations in the buffer, starting with index 0 and ending with index n minus 1. Once I get to index n minus 1, the next index is back at 0 again. That's what we mean to be circular. And you can see that constraint is forced down here. We increment the index, in this case the in pointer is the right pointer, telling us where we can write into the buffer. And when we increment it, we do it modulo n. That's what makes the whole thing circular. And the consumer, which looks very much the same, goes off and it reads a character from the buffer using the output index, and then increments the output index modulo n. So that's what the producer and the consumer look like. Now, left to their own devices here, there's nothing that controls the execution here. There's nothing that's enforcing any of the precedence constraints. So what we're going to do now is to slowly evolve this program to include a mechanism for enforcing the precedence constraints that we want. Okay, so no precedence constraint. The receive could happen at any time. It's happy just to read from the buffer and increment the output pointer, whether or not the producer has produced anything. So there's clearly a bunch of things we're going to need to fix up here. And now we're going to introduce our elegant solution. It's called a semaphore. And I've talked about signaling. Well, you can see, okay, so a guy with signal flags. And so we're going to come up with a very elegant technique to allow the producer and the consumer to communicate about the state of what's in the buffer and what's not. So we introduce a new data type called a semaphore. You can think of it at some level as an integer. It's just a number. It goes up and down. It gets incremented and decremented. But we're not allowed to use it as an integer. We're not allowed to use plus and minus operations on it or look at it directly. The semaphore, there's only 2 operations you can do on a semaphore. One is called wait, and the other is called signal. Right, and it's tempting to solve various sorts of problems we might give you by thinking of it as an integer sometimes and dumping a 0 into it, or manipulating it as if it's an integer. You shouldn't do that. The only way we can ever touch any of the value in the semaphore is either using the wait operation or the signal operation. So wait is pretty simple. What wait does is that it basically waits until the semaphore is non-zero, has a non-zero value, and then it decrements and returns. So when if a procedure calls wait, it doesn't necessarily, wait may not return right away. It will stall inside of the wait, waiting until the semaphore is non-zero. And when it is, it will decrement it and return. Everybody got that? Okay, and signal is correspondingly simple. Signal simply increments the semaphore. So it adds 1 to the semaphore. But again, remember that we want to make sure that we always access the semaphore using wait and signal. And there's a very good technical reason for that, which will become apparent in just a moment. Yes?
So you say wait semaphore 2, so it just returns semaphore now is equal to 1, and it doesn't make anything with it?
Yeah, so if in fact it can decrement it right away and return right away, it will. And we'll see that in operation too, right? So remember, the argument to the semaphore, the argument to wait and signal is the name of a semaphore, And you should think of the semaphore as having an integer value. Okay, in this case, you can see we initialized it to k. And so what we're doing is that we're managing a resource that has sort of k parts to it, and that'll become more obvious. But technically, if we initialize this to k, what we're doing is the semantics of weight and signal implement the precedent constraints that we're talking about. In other words, that the way the semaphore works is that the ith signal has to happen before the ith plus kth weight. That's maybe a little abstract. We'll have a good practical example, and it'll become much more clear what's happening there. Okay, so the thing you should keep in mind is that this is a data type that has a constrained set of operations, weight and signal. You should understand the semantics of weight. You know, if it's non-zero, if it's greater than 0, decrement it and return. If it's not greater than 0, wait, okay, until it is, and then decrement it and return. And signal, there's no blocking, signal always just increments and returns, so there's no blocking. So the wait might block until it can finish the decrement and return. Okay, so that's the basics here. So this was, you often see in the literature, weight and signal are called P and V, which stand for the Dutch words. You can see the Dutch words down here. So this whole mechanism of semaphores, this data type, and it's used to synchronize communicating processes, to enforce precedence constraints, was invented by a guy named Edsger Dijkstra, very famous computer scientist, at, was it ETH? No, not ETH. Technical University at Eindhoven. I think that's where he was. I don't know, does Steve remember where he was? Anyway, no, Steve doesn't. Anyway, P and V. You see P and V. So in the literature, you can see P and V, and you can actually decide whether that means that you know that should mean weight and signal. Okay. So we have a pool of k resources. In the case of our n character buffer, we have a pool of n resources, which are the spaces in the buffer, is the number of characters in the buffer. So what we're going to do is there's this sort of notion of you have in shared memory, you have the semaphore, and then in each process, if you want to sort of use one of those k resources, you can go ahead and wait on it, and if there's one of them available, in other words, if the semaphore is greater than 0, you can decrement it, which means that you grabbed one of the k resources. So now the number out there is 1 less than it was because you've taken one, and you can use it. And when you're all done, you signal that you're done. So you wait until it's, you can use it, and then you signal when you're done. Right? And these two operations manipulate the value of the semaphore. Again, sort of, this is all, I'll show you a nice example now that'll show these things in use. So you think, so what is the value of the semaphore? It tells you the number of resources that are left in the pool. Right? If there's 5 laptops that can be checked out, everybody who wants to use a laptop does a wait on the laptop semaphore. And at that point, once wait returns, that means there is at least 1 laptop, maybe all the way up to 5 laptops in the pool. You get your laptop. The number of laptops in the pool gets decremented by 1, and you keep going. If you try to ask for a laptop, if you do a wait on the laptop semaphore and a 0, there's nothing for you to do. There's no laptop for you to use, no resource available. So in fact, you have to wait, and the wait will block until somebody somewhere else signals that a laptop has been returned to the pool, at which point your wait can now succeed. Okay. So we're going to use our bounded buffer problem here, use semaphores in our bounded buffer problem. We're going to use that to indicate the number of characters that are in the buffer. So initially the number of characters in the buffer is 0, and every time the producer produces a character, it will signal that there's another character in the buffer. So the resource we're managing is the number of characters available in our shared buffer. Similarly, the consumer is going to do the wait. So it's going to wait for a character. That makes sense, right? I mean, it waits for a character. So it's basically using the semaphores, checking that semaphore value. And when that semaphore value is greater than 0, it's going to say, aha, I'm going to consume one of them. So the wait will decrement the value of the semaphore, which is the number indicating the number of characters in the buffer, because I'm about ready to take a character out. Right? So this pretty much guarantees that the receiver can only receive characters that have been put into the buffer. So notice we put it into the buffer and then do the signal, meaning the character is already in the buffer. And then here we wait to see that the character is in the buffer, and then we take it out and consume with it. So does this solve our problem? Yes?
Wouldn't you want to take it out before you do the decrementing? Because otherwise...
No, in other words, you don't know. So basically, waiting to see that it's non-zero and decrementing happens as a single operation. And you'll see this is important because if we have multiple consumers and multiple producers, we will use this same scheme, and this will actually work fine. But it's important that both the waiting for it to be non-zero and decrementing happen, as an atomic, uninterruptible single operation. So wait is basically saying, not only am I going to wait for something to be available, but when I return to you, not only was it available, but you got it. All right, so wait combines both of those semantics. Is there something available, and can I have it, please? Wait does that in one atomic operation.
But then couldn't the producer stick a new character in between the wait and the C equals buff out?
Well, so one of the problems we might have here is that there's actually two precedence constraints we were interested in. One is that the consumer not consume a character that hadn't been produced, but you just mentioned the other constraint, which is what? What's the other thing we need to guarantee? I'm sorry? I'm not sure I understand. Say a few more. Well, that's guaranteed by the FIFO, in a sense, of the code. The code always is guaranteeing I'm taking them out in the same order they're put in. But there is a problem here. What happens if we keep running and running and running, right? What can go wrong? There's nothing in here that prevents the producer from producing too many. The consumer is guaranteed not to consume anything that's not there, but there's nothing in this code. So there's one precedent constraint, right? We wanted the ith receive to happen after the character had been sent. The ith character had been sent. But now we have to make sure that the producer doesn't produce more than n ahead, right? Because otherwise the buffer will overflow. Right? And so the answer is, well, nothing prevents this from happening, and that's usually bad. Right? So it turns out that the semaphore was a great resource for dealing with making sure that the consumer only consumes after the producer is produced, but there's nothing that keeps the producer from overproducing. Right? So we have that precedence relationship that was established by the character semaphore. We need this one, which makes sure that the sender can't get too far ahead of the receiver. So we're going to introduce another semaphore that manages the space in the buffer. So the first semaphore managed the number of characters in the buffer. The second semaphore will manage the number of spaces in the buffer. Right? So when the consumer consumes a character, what does it produce? It produces a space. Right? Think of the producer as converting spaces into characters, and the consumer is converting characters back into spaces in the buffer. That makes sense? Right? And so it's the second semaphore that we'll use to implement the other precedence constraint. So initially, there are 0 characters in the buffer and n spaces. And what we're going to do is the producer now will have to wait for a space. And initially, if we start both of these programs running at once and the producer starts right away, what will happen? Will the wait on the space semaphore succeed, or will it block? It will succeed. Why will it succeed? Because space is initialized to n, so we basically can go around this loop how many times before it will stall, assuming the consumer is not running at all? N, right? After we've gone through n times, the space semaphore has been decremented down to 0. We've used up all n spaces. And after we've done that, what do we expect the character semaphore to be? N, right? So what do you think the sum of chars plus n should be at any given moment? N. right? Everything, we should completely account for the buffer. It'll be partly spaces and partly characters, right? So that's sort of the invariant here. And you can see that the way this sort of works is after we consumed a space, then we're going to produce a character, right? So there is a small gap in here occasionally where they don't, at every specific moment, exactly add to n. Okay, but after I consume a space, I'm going to produce a character. And so after I've run this punch of code here, that relationship is reestablished. And over here, I'm going to consume characters and produce spaces. So now we have both relationships. Okay, so it works with a single producer and consumer. Okay, so let's try a slightly different example, which will sort of motivate. Suppose you and I have this great scheme. We're going to run over to Bank of America, and we're each going to stand in front of a machine. We're going to each try to take $50 out of the 6004 account. And the bank has carefully written some code that does this. You take an account number and an amount, and the bank says, well, this is great. We're going to pick up the balance and subtract the amount you're trying to withdraw and put it back in the balance. That all's great. And what the bank imagines will happen is that there'll be a process that's dealing with the first ATM and a process that's dealing with the second ATM. And there's a sort of notion that fine, you do your transaction, and then I'll do my transaction, and these two programs run, and everything is fine, and we end up subtracting 100. However, if the execution of the program interleaves in the wrong way, in other words, if we stop running process 1 on the bank's big time-sharing system, right after it's loaded the balance, and then process 2 comes along and handles my transaction before we completed your transaction, you can see what's sort of happening here is that I'll subtract $50 from the account, but you'll subtract $50 from the account when your process resumes execution, but you'll be using the old balance. Right? So in the end, we'll end up with $100, but the bank will think that the account has only had $50 subtracted from it. All right. So I think we should all do a field trip right now and see if Bank of America has attended lecture 21 in 6004. Okay, or at least the people they bought their database from. Okay, so what is it we actually want to have happen? What is it we want to guarantee? What's a simple way to guarantee that we never have these bugs? And the simple guarantee that we want is the notion that once I start executing these 3 instructions, we load the balance, we manipulate it, and we restore it back. Those run as an uninterruptible unit. No other program is allowed to start manipulating the balance. Read it, write it, do anything to it, okay, as long as I'm manipulating the balance. The balance, in some sense, is undergoing some amount of change by process 1, and it doesn't want to, either the change should not have started, or the change should be completely finished, and no one should be allowed to mess with the balance in between. Right? That's how we're going to guarantee we can't both sneak out $50 at the account and end up richer than the bank is sort of going, well, this money, and it's all in the 6004 account too. I don't understand. So, okay. So modern systems, they implement the so-called transaction semantics, which sort of guarantees the atomicity of a sequence of operations. It turns out we can use semaphores to implement that semantics. So what we have here is, here's the code, and we want to add some semaphores to it. And what we notice is that we want to have a different sort of precedence relationship, which is that A and alpha either happens before beta or beta happens before alpha, but they can't happen concurrently. Right? We definitely want one to happen before the other. We're not particular about one before the other. And in fact, we don't want to introduce the constraint that alpha always happens to happen before beta. We would like to have the flexibility of them happening in either order, but we don't want to have them happen at the same time. And so what we're going to do is we're going to introduce this notion of a lock, a simple semaphore that gets initialized to 1. So this might be a binary semaphore. Binary because the value of this semaphore is either 1 or 0 at any given moment. And so think of this as a resource we're managing a single resource, which is the right to be in this chunk of code. That's the resource we're managing, the right to run these instructions. right? And we're going to allow exactly one person to have that right at any given time. Think of it as a token. I'm going to hand out the token, and I have to wait until you hand it back before somebody else can run. Okay, so we wait on the lock, we do whatever we want, and now if everybody who touches balance waits on the same lock, no one will be manipulating the balance, okay, without having first acquired the lock associated with this balance variable. Okay, and then when we're done, we signal, which means we'll free up the opportunity now for someone else to potentially manipulate this. Okay, so access to a critical section of code that we want to make sure runs without any possibility of other people who want to manipulate the same piece of shared memory getting in and sort of starting when I'm only halfway through. This is what's called mutual exclusion, okay, or the notion of exclusive access. Only one of us can be running the code at any given time. An interesting question is, if you were Bank of America, what sort of lock should you have? Should you have one lock for, all of Bank of America? Right, what would be the problem with, having one lock? Every time anybody in the whole world manipulated an account, somebody had to say, I have the account manipulation lock. Well, yeah.
There's probably millions of Bank of America customers.
Right. So what you're saying is, well, that produces a lot of unnecessary precedence constraints, right? The trouble is, by locking everybody out of all their balances, I'm not manipulating all the balances, I'm only manipulating one balance. Okay, what about a lock per account? Well, that would get the job done, but it's a lot of locks, so that might be, in a sense, expensive. And then maybe there's intermediate things. Where we might have fewer than one lock for everything, but rather than have everybody have their own lock, every account have their own lock, we might have a lock for all the accounts that are, were originated in the Bay Bank down the street here, or something like that. So it cuts down on the number of locks a lot. There's actually a famous example of a global lock that has wreaked havoc with people's plans to run concurrently. It's in Python. Python has a global lock, so whenever you're about ready to manipulate things in Python that will cause the state of some data structure to be inconsistent for a moment, you acquire this global lock, which is fine when there's a single program running, but if you try to run multi-threaded in Python, you spend almost all your time waiting on the stupid global lock. So global locks in Python have, are an example of a convenient, remember a moment of convenience, a lifetime of regret? Well, here we see it again, sort of cropping up. Our particular problem in the producers and consumers having to do with mutual exclusion is the following thing. Suppose we have multiple producers, right? And they're both trying to produce characters into a buffer. So I'm having lots of people producing information that we have a single consumer for, right? So we have lots of producers, and they all want to manipulate the buffer themselves. And you can see what they do is that they're in the process, there's a sort of a two-step process. You put something in, and then you change the pointer. And the trouble is, if these guys interleave in the wrong fashion, like so, we can end up with reusing the same location twice and then leaving a blank in the buffer. So this ends up putting the character C in the same location of the buffer, but then incrementing the in pointer twice. So there's an example of interleaving of these shared variables, which is the buffer itself and then the in pointer, which is shared among all the producers, of interleaving that we want to avoid. So we need to use having some way to prevent this particular piece of critical code from being executed by more than one procedure at a time. And the way we're going to do that, we're going to introduce this mutual exclusion semaphore, which we almost always conveniently name mutex for mutual exclusion, right? As before, or a lock or something like that, we initialize it to 1, indicating we're going to allow one piece of the code. And you can see we do a wait and a signal, okay, around the code. So any of the producers that are busy manipulating the in pointer, okay, are waiting on the mutex. And any consumers that are busy waiting on the, want to manipulate the out pointer, use the mutex to guarantee that more than one consumer isn't in that critical code at the same time. So this code actually implements an unnecessary precedence constraint. What is that unnecessary constraint? Right. The idea here is we're trying to prevent multiple producers from screwing around with the in pointer at the same time. Over here, we're trying to prevent multiple consumers from screwing around with the out pointer at the same time. Okay, but we've used a single mutex. Right, so in some ways, maybe the best implementation of this code would have one mutex for producers and one mutex for consumers. You'd only have a shared mutex if you were manipulating the ins and outs, together. If there was code that used out over here and code that used in over there, then you'd want a single mutex. Everybody sort of happy with that? So if we're, all of a sudden we didn't know about semaphores 35 minutes ago, and now we're sprinkling them all through our code, and we're actually able to now produce very sophisticated constraints, okay, about what can run in what order. And we can even allow the producer to get up to n characters ahead. We can guarantee that we only run critical sections of code in one process at a time, make sure it runs to completion. Okay, so here you see the power of semaphores. We've implemented both precedence relationships, and that had to do with the characters and space semaphores, and mutual exclusion, which we use the lock or the mutex semaphore for. Okay, and so almost certainly we'll be asking you problems having to do with multiple processes running and say, we want to make sure that, here's a process printing C, and a process printing A, and a process printing T, and we want to make sure it only prints cat. Well, then you can say, well, we want to print the C before the A and the A before the T. And how do we guarantee that with 3 independent processes? Well, some semaphores, some weights and signals. So you have to figure out where to put the weights and signals, okay? And whether you're doing precedence relationships or mutual exclusion, you have to figure out the initial values of the semaphores to make sure that the right thing happens. It's a little puzzle, but they're usually pretty fun to solve, and they turn out not to be all that hard to solve once you sort of get the basic idea. Yes? If you have multiple consumers.
Does that mean that all the consumers are within the same process, or each consumer is a different?
Each consumer is a different process, but they all share access to this set of semaphores.
Right. So doesn't that mean that if one consumer, if one process uses a piece of data, then the other process can't because it's how it takes the
Right. So in this particular arrangement, each consumer is consuming one of the characters from the buffer, and the other consumers don't see that. So that would only really make sense if somehow each thing in the buffer could be processed independently by the consumers. Does that make sense? In other words, that the consumers are seeing some sampling of the things in the buffer. They don't necessarily see them in consecutive order. Every consumer doesn't get to see every character. At least the way this code is written. Okay, how do you actually implement semaphores? And we'll talk about a couple ways. The big thing is that weight and signal themselves need to be atomic. In other words, they have to, as you say, check the variable to see if it's non-zero and decrement it. And they have to do that without somebody else starting their check and decrement, because we can get into the same problem that we got into with the bank balance. So we have a couple schemes. We can implement them in a kernel's supervisor call, which has the advantages once you get in the kernel, no interrupts can happen, only the kernel is running. So that's a very simple way to guarantee atomicity from the user's program point of view. We can add an instruction to the hardware, which I'll show you in a second. Actually, you already added this instruction as part of quiz 3, as it turns out. Or there's actually a clever way just using reads and writes to memory, but it's actually never used in practice. So it's usually one of these first two implementations, a kernel call or a special test and set instruction. So the kernel call looks very simple, right? I mean, here's the weight thing. You can see it going off. We put the address of the semaphore variable. So we don't actually hand in the value of the semaphore. That'll be up for the kernel to check. What we do is we say, here is the thing we put into R0 is in fact the address of the semaphore. The kernel then uses that address to access user's memory, checks the value. If it's if it's less than or equal to 0, in other words, we need to stall, you can see it backs up, and so that when we re-execute the user program, we'll re-execute the wait supervisor call again, and then we go call the scheduler saying, I'm going to go to sleep, wake me when somebody has put something into this, incremented the semaphore. And down here you can see the signal, which works very much the same way. We pass in the address of the semaphore, increments it, and then does a wake up on that address. So remember the sleep and wake up mechanisms that guarantee in a time sharing system that we don't bother running you if there's really no sense. But the big thing is that this notion of checking the semaphore and then, and in this case, decrementing it. Okay, because this is in the kernel, we can't get any interrupts between this check and this decrement. So that's what I mean by them being atomic. If I execute the check, I can guarantee that I'm going to decrement it. Okay, so in this particular case, the semaphore should never get below 0, right? Because if it was equal to 0, I should never decrement it. There's no accidental somebody checking it and then later decrementing it, thinking it was still non-zero. I mean, if I check it, then I'm going to decrement it. Okay. Another way, and this is actually the instruction you implemented in quiz 3, the test and clear, where the atomic piece of the operation you can see down here, which is basically I get back the old contents of the memory location and I set it to 0. And that turns out to be enough to be able to implement a very simple binary semaphore. And once you have a binary semaphore, something you can use for mutual exclusion, then you can have a critical section of code that goes off and takes FFTs or whatever you want for this on the semaphore. You can implement a much more, an integer semaphore, that involves actual incrementing and decrementing, so long you're guaranteed that the sequence of instructions that you're using to manipulate the semaphore is guaranteed to be atomic, that only one process can be in this code at once. So test and clear. All right, so one last interesting problem to solve. Suppose we're doing a transfer. Okay, I'm transferring money from 001 to 004. You're transferring money from 004 to 001. We both walk up to the, I haven't been that skinny in years, so. And I was never tall to begin with, so okay. Not me. One of you handsome folks, you go up to the teller machines and you run this code. You can see they're very careful locking the accounts and everything. So this has a problem called deadlock. What is the problem? See if you can think through what the problem is. Think of each person coming up and running the code. Notice the order of the arguments is different. The first argument here is 6001. Second argument here is the first argument here is 6004. So imagine I'm running the code and you're running the code. So what's the first thing you do? You're this person here. So you're going to do a wait for a lock on the 001 account. And you get it because you're not manipulating the 001 account. At the same time, I'm running down here. I've changed gender and have more hair than I usually do. Whoops. I've gone off and I've gotten a lock on 6004. Now what's the second thing each of us tries? And will I succeed? Will you succeed? No. Why not? Because the other person has the lock. So now we're stuck, right? You sort of look at this and say, well, this is a crummy idea. You've been touting semaphores as this wonderful panacea that solves all these problems. And now we have a slightly simpler, more complicated thing where what we're trying to do is to access two independent resources. And if you acquire the lock to one and I acquire the lock to the other, so we can manipulate them both, okay, our goal is for each of us to manipulate them both, what will happen now is that we go into what's called deadlock. We're stuck. None of us, there's no way for us to get out of this. Okay, so this is sort of the toy problem that you always hear about, is the dining philosophers. There's a big table. In this case, it has 5 philosophers. You should amuse yourself by figuring out who each of the philosophers are. And then there's 5 chopsticks. And the goal is that you pick up one. They wait for their left chopstick. They pick it up. They wait for and pick up the right chopstick. And now they can eat. Okay. Although my experience of using chopsticks to eat turkey has not been successful, but these guys are skilled, obviously. Okay, and they can eat. And what's the problem here? How is this an example of deadlock? What can go wrong? Yes?
Well, one of them tries to take the left thing first,
Right. They all reach out and grab their left chopstick, and then they all look at the table, and you go, oh, all the chopsticks are gone. Right. So notice that there are 5 chopsticks and 5 philosophers. Okay. So this is the deadlock situation, right? Just they're all sitting here, and here's so basically, since everybody can grab one chopstick, and only one person can have the chopstick at a time. So there's this notion of exclusive use of a resource. This notion that once you grab the resource, you're not going to let go until you're done. So it's hold and wait. You're going to waiting on something else, and you're not going to let go of the chopstick that you have. Okay, and there's no preemption. There's no way to say, okay, give me back the chopstick. We're going to have to solve this problem some other way. So now we have this circular wait going on. And, the turkey is saved, sort of. But the solutions, what are the solutions to this problem? And the answer is we either need to avoid it, we need to come up with a change in our strategy of using semaphores to avoid this problem, or we have to detect it and then, have the system sort of in some more global way reach out and solve the problem for us. So we can write our code sort of naively, particularly if we're writing the code for all the philosophers. We can figure out a better piece of code that solves the problem so that we avoid it. But if we have uncooperative processes that are still might go into deadlock, the best we can do is discover that they're in deadlock. And we can do that because we see that they're each waiting for something that somebody else already has and will never give up. Okay, and simply, kill the process or restart the transaction, something like that. Okay, so there's a simple way to solve this problem, which is to number the chopsticks, and instead of going to left and right, simply pick the lowest chopstick first and then your highest one. Right? And this simple notion of ordering, coming up with a total ordering of all the resources that you're competing for, and always acquire them in the same order. So what's the solution with the 001, 004 problem? Even though both of us naively would want to access our first account and then the second account, will in fact access the accounts in the numerical order, which means that if we're both trying to manipulate 001 and 004, each of us will try to get the lock for the 001 account first, and then the 004 account. And by the fact that we've now placed this global ordering, we solve there's no possibility of deadlock anymore, because the person who gets the 001 account will also then get the 004 account, because the other person is now waiting for the 001 account. Right? So does that make sense? So this notion of a global ordering is good, but you basically have to agree with everybody on what the order is. And you can imagine in a large operating system, when there's just lots of resources to be managed, right, the idea of going up and saying, okay, we have to assign every resource in the system a unique increasing integer, those are the sort of things that software people tend to want to avoid, this sort of central authority that's sort of organizing some sort of relationship among everything that's possible, turns out to be sort of cumbersome. Okay, so this is a solution that works when you can write all the code, like the bank can. It works less well if you're trying to manipulate two things in the operating system, this device and that device, and you don't have control over all the drivers and stuff like that. So the deadlocks can be a substantial problem. And it's a real pain because you're going along, your system freezes, and you say, well, is it a loop in the kernel, or is it perhaps some deadlock situation? So if you go examine all the status fields, you can say, wait, process 1 is waiting, has a resource and is waiting for something, and process 2 has the resource that process 1 is waiting for, but it's waiting for something else, and you can sort of identify the circular waits. Okay. So it turns out semaphores are a really neat idea, with the exception of trying to deal with this deadlock problem, and that you have to think a little bit about. But if in many situations we don't have the deadlock problem, we have very simple precedence constraints we're trying to have, or mutual exclusion. So we've introduced a new data called semaphore, a new data type called semaphores. It has a wait operation and a signal operation, and we can parlay that into basically synchronizing communicating processes, which is sort of a pretty neat thing to do in the modern world. Okay, stop there. Next time, drum roll please, we're going to start working on our pipelined beta. And by that time, almost, you'll have finished your unpipelined beta. So good luck with that, and we'll see you Thursday. And of course, recitation tomorrow.